Hello and welcome back to High Peak Education. I would like to perform a calculation where a charged particle is moving in a uniform magnetic field such that the magnetic force exerts a centripetal force on it. So let's read this problem. So part A proton moves at 7.50 times 10 to the 6th meters per second perpendicular to a B field. The field causes the proton to move in a circular path of radius 0.800 meters. What is the magnetic field strength? And then B, what is the period of the circular motion for the proton? So let's start to work this out. So first of all, if a proton is moving perpendicular to an B field, we first know that its velocity is 7.50 times 10 to the 6th meters per second, and it's perpendicular to a magnetic field vector. So this is a vector, and then this has a magnitude of like so. Since it's perpendicular, I think we have the sine of phi being 1, because phi is exactly 90 degrees. Okay? So that's the idea. The smallest angle between the two of them is 90 degrees, and this maximizes the magnetic force. Also, we know the field causes the proton to move in a circular path. So that means it has to be a uniform magnetic field. That is, the deflection is constantly equal magnitude, but changing direction such that it's always deflecting the particle in a circular path. So the radius of that circular path is 0.8 meters. And we want to know the magnetic field strength. That is the magnitude of this magnetic field. Well, if you recall, our basic picture is something like so. Now, back in the lecture slides, I showed a positively charged particle going counterclockwise. But that's because the magnetic field, I think, was into the page. Let's see if we can produce a positively charged particle that's going clockwise. Well, if that's going to be the case, the velocity of this positively charged particle should be tangent to this circle at any point of interest, and that's the direction of QV. Now, if B is out of the page, I believe, so if the magnetic field is something like so, where there's these dots, it's out of the page, everywhere and uniform. So these are meant to represent magnetic field vectors. So if it's out of the page, QV cross B out of the page, I think the centripetal force should be directed towards the center, and that's also the magnetic force. So that's F sub B vector. Okay? So that's the idea. And if you recall, when you equate the magnetic force vector and the centripetal force vector, you get one of the v's to cancel, and you get this special equation. R is equal to mv over qb. That's the radius of a charged particle moving in a uniform magnetic field. But let's solve this for b. So we need to multiply b up and divide r down. So this should be b, the magnetic field magnitude is mv over QR. And I think we have all the values. We can just put the numbers in. So B is equal to, now the thing is, it's a proton. And I didn't mention that before, but we know what the mass and the charge of a proton are. So I believe a proton should be 1.67 times 10 to the minus 27th kilograms. You can look that up online, in a textbook, engineering manual, etc. The velocity is about 7.50 times 10 to the 6th meters per second. Let's divide all that by the charge on a proton. Now the charge on the proton is a positive fundamental charge. That's 1.60 times 10 to the minus 19th coulombs. You should know that number for this class. It's used a lot. And then the radius is 0.8 meters. Okay, so let us perform this calculation. So now I'll do alpha F1 n over d, numerator over denominator. I'll do 1.6 0.67 times 10 to the minus 27th power, that's the mass, multiplied by the velocity times 7.5 times 10 to the 6th. I'll do arrow down to get 1.6 times 10 to the minus 19th times 0.8. Okay, so let us write this down. It's about 0.0979. Okay, so it's about 0.0979, approximately 0.0979. And that's magnetic field strength. That's in Teslas. That's a pretty reasonable laboratory magnetic field. Most laboratory magnetic fields are on the order of about maybe 0.1 Teslas, a tenth of a Tesla. Okay, so that seems entirely reasonable. Now, how do we solve, now that we have part A correct, for the period of the circular motion of the proton? Well, if you don't have the equation memorized, we know that V is equal to omega times r, angular velocity times radius. So if we put that in, notice that a radius will cancel from both sides. So we'll have 1 equals m omega over qb. So that's omega is equal to qb over m. And recall that period is 2 pi over omega, where omega is the angular velocity. So if we put that expression in, we should have that period is equal to, let's see, that's going to be 2 pi m over qb. All right, now we have all the numbers. Remember, the period and the angular velocity are independent of the radius. That's why cyclotrons work, because they don't really depend upon the radius. So let's put the numbers in. So we need 2 pi times that mass, 1.67, times 10 to the minus 27th kilograms. All divided by the charge times the magnetic field strength, and that's again 1.60 times 10 to the minus 19th coulombs times that magnetic field strength of 0.0979 Teslas. Okay, so let's get this value for the period. So we clear, let's do alpha F1, do a numerator over denominator stack again. Let's do 2 times second pi. Let's do times 1.67 times 10 to the minus 27th kilograms over 1.60 times 10 to the minus 19th coulombs times 0.0979. And that's Teslas. So we're going to get, let's see, 6.70 approximately if we round to 3 significant digits. 6.70 times 10 to the, looks like minus 7th seconds. So this would be like 670 nanoseconds. I mean, that's extremely short period of time. So this proton is actually going around quite fast. Okay? But that makes sense because, again, this is what happens with these very small charged particles. Okay, so that ends this problem. Thank you very much for your attention. Please smash that like button if you like this content. Please subscribe to the channel to grow the channel. Please share this amongst your social network. And I want to thank you for watching High Peak Education. I will see you in the next video.